Okay, Assalamualaikum and very good day everyone. So this is lecture on reaction kinetics. Okay, let's consider this reaction. We have alpha A reacting with beta B to form epsilon C plus lambda D. Okay, so the reaction is conducted in a closed system. And now you are being introduced to a new term R. R is a rate of reaction. And in order to calculate R, okay, the rate of reaction, we need to know the stoichiometric coefficient for each reactants and products. Okay, and as we see here, R equals to minus 1 over alpha dA over dt equals to minus 1 over beta dB over dt plus 1 over epsilon d concentration of C over dt equals to plus 1 over lambda d over dt. Okay, so we need the concentration of A, B, C, and D. Okay, and we need also the information regarding the number of moles of A, B, C, and D. Okay, alpha, beta, epsilon, and lambda, those are the stoichiometric coefficients or number of moles for A, B, C, and D respectively. Negative, we have a negative sign here for 1 over alpha. That negative indicates for the rate of decomposition or consumption of reactant A and B, and positive indicates the rate of formation of products C and D, because in a certain reactions, usually the reactants A and B keep on decreasing and the products, okay, keep on increasing. So positive indicates the rate of formation of the products, in this case C and D, and negative indicates the rate of decomposition or consumption of reactant A and B. Okay, let's see problem 1. For problem 1, we have A and B reacting to form 2C, okay, 2 moles of C. 1 mole of A reacting with 1 mole of B to form 2 moles of C. Okay, it is identified that 0.003 mole of B exists after 0.01 seconds. The reaction is conducted in a batch reactor at a constant volume of 0.3 liter. So let's tabulate this data. Okay, from this data, we need to calculate the rate of consumption of A and B and the rate of formation of C. Okay, we have a 4-column here. Okay, we have the first column, at the first row we name it as species, and we put all the species which exist in our chemical reaction. We have A, okay, followed by B, and the 4th column we put there as to C. Okay, as you can see here, I also write down the number of moles of each molecules. Okay, for number of moles, it is stated here that 0.03 mole of B exists. So we have no information regarding A and C, but we have information regarding B. We write there 0.03 mole of B. Okay, under B, add a row of mole. Okay, and we have to calculate the concentration of B. Given in the problem, okay, the reaction is conducted in a batch reactor at a constant volume of 0.3 liter. In order to calculate the concentration, we need to divide mole over liter. So we have 0.03 mole over 0.3 liter, which is equals to 0.1 mole per liter. Okay, so that is the concentration of B. Now, concentration of B is 0.1 mole per liter. Okay, and it is stated that the rate of consumption of B is negative 10 mole per liter per second. How do I get that? Okay, you have to divide the concentration over time. which is 0.01. Okay, we divide 0.1 over 0.01, then we have negative 10 mole per liter per second. Negative indicates the consumption of B. Okay, so that's why I put a negative there. So basically, we are working at the column for B. We have to settle for B before we can predict the value for A and C. Okay, now we know that, and then we add a value of X. If you look at the far left, okay, for the first column, we have species, mole, concentration, rate, and also value of X. Now, under the rate, okay, at this stage actually we haven't filled up the rate for A and C. Okay, we are just solving for B. So now we introduce X. Okay, X equals to 10 because we have just solved for B. Okay, X is 10, which means 1 mole equivalent to 10. And A, in the equation we have 1 mole of A. So when X equals to 10, A also equals to 10. Okay, so as for C, there is 2 moles of C. So 2x. 2x equals to 2 times 10, which is 20. Okay, so let's go back to A. Okay, if you look at A, at the row of rate, now we can fill up the information there. So rate of consumption of A is negative 10 mole per liter per second. Okay, negative because A is being consumed, same as B, it's negative. But okay, for C, for column C, at the row rate, okay, it's called rate of formation of C or rate of production of C. Okay, now it's a positive 20 mole per liter per second. Okay, so this is how we can solve for problem, okay, if we are being given the mole, the time, and also the volume, okay, for a particular substance or molecule. We can solve for the others, for other substances or molecule in the same chemical equation. Okay, okay, this is a second problem. Okay, problem 2. We have 2A gas, okay, decomposed to form 2B gas plus C. Now, the rate of formation of B is given as 0.2 mole per liter second. Okay, the question is determine rate of consumption of A and rate of formation of C. Okay, now in this kind of problem, it is easier because the problem has stated the rate of formation. Therefore, we don't have to calculate the rate. Okay, we don't have to calculate the concentration, and we just have to straight download the table as you can see here. Okay, and we are going to calculate the rate of consumption of A and C straight away. Now, from the chemical equation, we have A, B, and C. We have 3 molecules, so we write down species first, okay, and we write down 2A at the second column, 2B at the third column, and 2C at the fourth column. Okay, the respective chemicals which exist in the equation. Now for rate, let's focus to B. Okay, so ignore A and C first because the information from the problem, okay, gives the information regarding B. So rate of formation of B is 0.2 mole per liter second. Okay, now in the chemical equation there is 2B. So value of x here is 2x. 2x equals to 0.2. Okay, 2x equals to 0.2, so x equals to 0.1. Okay, 0.1. So therefore, for C, if you can see there for C, rate of formation of C is plus 0.1 because there's only one mole of C, and x equals to 0.1 mole per liter second. Now for A, we have 2 moles of A. So rate of consumption of A is negative 0.2 mole second, because we have 2a, which is equals to 2x equals to 0.2. Okay, so basically this is the method that we can use to calculate for A and C if we are being given the value for B. Okay, this is stated here, the conclusion from the previous calculation. Rate of consumption of A is negative 0.2 mole per liter per second. Negative because A is being consumed. Rate of formation of B is plus 0.2 mole per liter per second. Rate of formation of C is plus 0.1 mole per liter per second. Okay, rate law. For rate law, let's consider that we have an equation alpha A reacting with beta B to form epsilon C and lambda G. Okay, this is the same chemical equation as before. By definition, rate law is the expression that uses the concentration of reactants to its power. So we need to know the concentration of the reactants. In this case, we need to know the concentration of A and B. Okay, so rate law, we can express it as R equals to K times concentration of A to the power of 1 times concentration of B to the power of 1. Now, R means the rate law, K is the rate constant, concentration of B in the bracket of concentration of B in the bracket that refers to respective concentration of A and B. 1, which is the power to A, and 1 to the power of B, that indicates the order of reaction. The order of reaction respect to A and also the order of reaction respect to B. The number of order of reaction can change. It depends on the reaction itself. It can be 0, it can be 1 or 2. Okay, so the power of concentration of reactants can be 0, 1 or 2. 1 plus 1, which is 2, okay, if we take the value of the orders of reactions, which is 1 plus 1, it becomes 2. That is called the overall order of reaction. So in order to get the overall order of reaction, we just need to plus the respective order of reaction for each reactants. Okay, the order of reaction can be determined by the experimental method, meaning that experiments must be conducted to derive the order of reactions. Okay, as it's stated there, the order of reaction must be obtained from the experiments. So from experiments, we have sets of data where the data we have to analyze, and upon analysis, we can determine the order of reaction. Why are we so interested in the order of reaction respect to A and B? Okay, if we know the order, let's say if we know the order respect to A is 1, respect to B is 0, so we know that the rate equation becomes R equals to K constant times A to the power of 1, B to the power of 0. Now, in that rate equation, okay, rate law equation, only concentration of A matters, meaning that changing the concentration of A has impact on the rate of reaction, either to increase or decrease the rate of reaction. Changing the concentration of B has no effect because B to the power of 0. Okay, so that is the importance of knowing the rate law for a certain reaction. Okay, thank you very much. I hope that is beneficial for you. Okay, thank you. Assalamualaikum.